Okay, yes, excellent. So we're starting again. Our journey in vector spaces, and I said the fundamental of the vector space is Rn. We've seen examples. This is the Euclidean space, dimension n. Sometimes we use d, sometimes we use n. We have to be flexible on these. Okay, so this is the Euclidean space of dimension n, also known as the n-dimensional Euclidean space. We've seen other vector spaces like polynomials of degree k. We've seen also vector spaces that are not necessarily finite dimensional. For example, the space of sequences with real values, which we've seen last term. Okay, so these are polynomials. Degree k, so that this one has informally, so that it has dimension k plus 1. This one here, so it cannot be attributed to any dimension because simply we cannot find. So because we can find systems of independent elements that are larger and larger and larger without any bound on that. That's essentially how we find dimension of the vector space, which we're going to do today. So this is just as a reminder, this is the space of real values, sequences, infinite sequences. Okay, so that's remind. Okay. Those who haven't seen these objects too many times, that this is usually when we say sequence, we mean infinite sequence. When the sequence is finite, like here, we would say it's a finite sequence. And bear in mind that this is just a generalization of this one here, okay, where n becomes essentially infinite. Okay, so this is, some people like to write this like this, okay, but this is a bit vague because, as we've seen, there's many types of infinity. Okay, so we don't like this notation because it's not very precise. Yeah. There's of course many other vector spaces that we shall not describe in this little recap. Okay. And it's always a good idea to think about vector spaces that are not necessarily Rn. Okay. So this is especially useful when we want to use these things for many practical applications. Okay. One thing that is concepts that we have introduced are quite useful are independent and therefore also dependent sets, also sometimes known as systems of vectors. So if V is a general vector space, okay, so what is a vector space? Vector space is could be any one of these characters here, or could be something else. Okay, the important thing is that it has some algebraic structure, which is basically being able to add objects to a vector space and to multiply them by scalars, or scaling. Yeah? So once you have that, then you can define a concept of dependent vectors. Okay, so when do we say that? So let's take a set of vectors. Okay, so let's call them v1, vk. Okay, so take some vectors v1, vk, and v. Okay. So as I said earlier, I'm denoting, I'm indexing vectors with super indices, okay? Because it doesn't make much sense to multiply vectors together in general. Some of them can be multiplied, for example, polynomials, but some of them do not multiply giving you vectors. Okay, you can multiply them; they will give you scalars, but it's a different type of multiplication. Okay, but vectors among themselves usually cannot be multiplied in a way to remain in the vector space and to conserve all the usual rules of multiplication. And therefore, we write a superindex in order not to clutter the notation with just sub-indices. All right, so assuming you have these, okay, and my convention, I remind you, is to write an ordered row array as a capital letter indicating the lowercase letter that's in there. Okay, so this is simply the quick way of writing that. And we say that v1 vk, for this set here, okay, so set v1 vk, and sometimes we just say that the matrix or the array v is linearly dependent. Linearly dependent if there exists, if and only if, for some set of coefficients, let's call them lambda 1, lambda k. So these are coefficients in R. We have the following. And also some of them are non-zero. Okay, so some of them may be zero, but not all of them. Okay, so not all zero. Not all. So I write it in words. Not all zero. We have the following. We have that a linear combination of these vectors is equal to 0. Okay, so this is R1 k lambda r p r is equal to 0. Okay, this is of course the zero v, right? It's not the zero number, it's the zero vector, right? So this is the definition of linearly dependent. And we saw last time that this is, in fact, a generalization of parallel. Okay, so this generalizes. This generalizes the concept of parallel vectors. In fact, parallel pairs. Because in fact, when we say linearly dependent, we don't talk about each single one of these vectors. We talk about the whole thing together. Yeah. So that's why we say the set is linearly dependent rather than saying the vectors are linearly dependent. Of course, in everyday language, it's easier to say they are, and we sometimes just say they are. Okay, but we mean that they collectively are. Okay. Same thing for parallel vectors. Okay, one vector by itself doesn't make much sense to talk about it being parallel, right? And two vectors can be not parallel or be parallel. Okay, so the parallelism is an attribute of the set of vectors, not of each single vector of them. Okay, so this vector here happens to be not parallel to this one, but parallel to this one. Okay. So when we say that two vectors are parallel, or a pair of vectors are parallel, okay, so reminder. What was the definition that two vectors are parallel? I give you two vectors, v and w. You say v is parallel to w if and only if what happens? Just think geometrically. Okay, so vectors are basically segments that are attached to the origin. Okay, we can scale them. We can add them with the parallelogram law. Yeah. And when we say that two vectors are parallel, if they point in the same direction, right? So essentially, if they're on the same line, right? So if one of them is a multiple of the other, right? So we say that two vectors are parallel if and only if there exists a lambda in different than 0 such that take one of them, so if both of them are 0, then you just declare them to be parallel. Okay, so 0 is it's trivially parallel to itself. Okay, but suppose one of them is non-zero. Okay, let's say V. If it happens to be W, then you exchange the roles. Okay, then you know that W has to be always. You can always express. You can always express the non-zero, the possibly 0 one as a multiple of the other one. Right. Okay. So that's basically what you can say. Okay. So this is basically the definition. Okay. So you see what this means? This means that when both of them are non-zero, which is an interesting case, it means that if this is, say, W, then V is going to be something which is maybe shorter, maybe longer, maybe pointing in the other direction, but it's always lying in the same direction. Okay, that's what it means parallel. Okay. Now, if you reinterpret this in actually not a maybe 0, okay, the non-zero coefficient is hiding here. Actually, it's a 1. Okay, because this is the same thing as saying that 1 W minus lambda V is equal 0, right? I'm just writing it in a form that resembles that. Okay? So if you want, it's like, let's call it lambda 0, V naught, plus lambda 1, V1. Okay, where lambda 1 is simply lambda. Okay, V1 is V, this one is W, and this one is 1, right? So I'm just rewriting this in a form that resembles that summation there. I'm starting from 0 just because it happened to be handier in this case, right? So you see, so basically, saying that two vectors are parallel means that they must be linearly dependent. Okay? So that's basically when you have two vectors. Okay, so the notion of linear dependence is a generalization of parallelism. Of course, for three vectors, this is no longer the case that they must be parallel. Let's make an example. Okay, so example: three vectors. Three vectors. And let's do it in R3 to be interesting, okay? Because any three vectors in R2 are going to be linearly dependent. Okay, that's another thing that we can also remark. Any three vectors in R2 must be linearly dependent. Again, meaning that the set of these three vectors must be independent. This is an R2, okay? So let's take an example of three vectors in R3, okay? I'm going to take the vector, say 1, 0, 0. Let me call this one 1, V2, because these are vectors in R, and we usually indicate them with a boldface letter. Okay, so that's why I underline it on the board. Yeah. So let's take V2 to this one here, and then let's take V3 to be so question, are these linearly dependent or not? How can we tell?
Is it parallel?
Which one is parallel to which? Not. If there were two, then we could use parallelism, right? But these are three. Okay. So in some sense, they are parallel. Okay. So there's something going on here. Okay. Except you don't see it straight away. Okay. That's why we do linear algebra. Okay. In order to go a bit more in the complexity scale. Okay. But let's just write down the definition and see what happens. Okay. So geometrically, let me tell you what's happening geometrically. So let's do a small picture. Let's draw these vectors. Okay, so one of them is, so I usually do 1, 2, 3. 1, 2, 3. That's 1, 2, 3. Okay, so 1 is 1. Okay, so we can do this. Okay, and the other ones are 0. Okay, so this is the vector. Let's take some color. Blue and orange. Okay, so this is V1. Okay, let's do V2. V2 is 1, 1, 0. This is 1, 1. It's here. Okay, so this is V2. And let's do V3. So V3 is here. Yeah? So V3 is it's long vector along the second axis. Okay, I don't have enough room to draw it, but it's here, right? So they all the three vectors are in the same plane, right? Which plane? They are in a xy plane, or 1, 2 plane, right? So that's essentially what the geometric meaning of linearly dependent. Okay, so with three vectors you could build the whole space, right? But these are not. This is not possible with these. Okay, that's the whole point of linear dependence and independence. Okay. So let's see this fact algebraically, okay, just to see the applied definition. So what does the definition say? It's saying that linear combination is equal to 0. Okay, so let's find. So we suspect these are linearly dependent. Okay, LD for linearly dependent. Yeah. Sometimes when we're in a hurry, just write LD. Yeah. So we suspect these are linearly dependent, and so let's find lambda 1, lambda 2, lambda 3. By the way, how do we write very quickly three scalars? We write the vector, yeah? So let's find, instead of saying this, the same thing we could have seen, we could have said vector in R3, right? Such that, not all 0, okay, not all 0. In other words, we want the vector lambda not to be 0. Okay, so the same thing. See, so that's why vector notation and vectors are useful, because you can say something very quickly. Okay, so lambda in R3 and lambda non-zero, such that the summation of this linear combination. Okay, so this was such that the linear combination, since it's a good reminder here, combination. So when you scale each single vector of a given set of vectors, you scale it, and then you sum all these scalings together. We call it a linear combination. Okay, so an expression of this form. Okay, so lambda I b I, so I going from 1 to 3, okay, is equal to 0. So that's basically what we're after. Okay, we'd like to find this. Now, if you recall, the matrix vector multiplication is nothing but rewriting that expression in a concise way. Okay, so if you take this V that I've written there, okay, in this very special instance, this is nothing but a quick way of writing the following. So this capital V is nothing but a quick way of writing this, okay, and lambda underline is nothing but a quick way of writing the column with entries lambda 1, lambda 2, lambda 3, and the so-called row column multiplication or matrix multiplication that was introduced earlier is nothing but a quick way of writing expressions of this type here. Okay, that's basically what a linear combination is. Okay, and this is just a quick way of writing a system, a linear system, right? And the linear system that we're writing here is nothing but this. Okay, so the notation is made in such a way that all you need to do, once you know that you're writing all your vectors as columns, okay, then all you need to do is to replace these with the columns that are written there. Okay, so in fact, what you have is the following. Okay, so this is the big and the expanded notation. Okay. So in fact, what I'm after is a solution of a linear system. Okay? And in fact, what I'm after is not just any solution of a linear system, because mind you, lambda 1 equals 0, lambda 2 equals 0, lambda 3 is equal 0 is a solution of this linear system, right? It's always a solution, right? If you take a 0 here, you multiply the matrix by 0, you're always going to get 0. Okay? But that's not what we're after. Because we don't want the solution to be 0. We want a solution that is not 0. So can you find a solution that is not 0 to this system? So, remind me, what does it mean when I say this system? Okay, just in case you've missed the classes, this is a linear system. Okay, so you multiply. So let's do this together. Okay, so let's multiply this row with this column. What do we get? You multiply 1 with lambda 1, so you get lambda 1. Then you multiply 1 with lambda 2. Okay. Then you multiply 0 with lambda 3. I'm not going to write this. Okay. You don't write the zeros. Actually, in many cases, we don't even write the zeros in here. Okay. I've written them just the ones. Okay. Here we have to write the 0, otherwise it will be really horrible. Okay, we don't write the 0 there. And let's look at the second one. The second row is basically this. Okay, so matrices are just a way of kind of condensing the information, not to have to rewrite the variables every time for every equation that we're writing. Okay, and finally, what is the last equation? Last equation is 0 equals 0. Okay, it's not very useful. Okay, so this is basically the deficiency in this system. Okay, so this system is kind of like deficient because it has 3 unknowns and just 2 equations, 2 useful equations. Okay, because one of them is useless. Okay, it is an equation. It is true, but it's useless. It doesn't have it doesn't convey any information on the lambdas. Okay, and that's exactly the key to the solution of our problem. So can you see a non-trivial solution, like a non-zero solution to this system? Well, let's solve it by hand. I mean, this is a very easy system to solve. Okay, so what is, for example, lambda 1 tell us? Okay, so the first equation. The first equation tells us that lambda 1 can be written as minus lambda 2. Right? Okay. And the second equation tells us that lambda 2 itself, or if you want lambda 3, can be written as minus a half of lambda 2. I decided to treat lambda 2 in a special way with respect to lambda 1 and lambda 3. Okay? It's just a choice. Okay? You could have decided to take another variable. Okay? I decided to be this one, right? Okay, now can you find a non-zero solution? Well, now it's enough to take any value for lambda 2 and you'll find a non-zero solution because it will satisfy that. Okay? So pick a nice value for lambda 2, I don't know, minus 1. You're happy with? So pick minus 2. So pick lambda 2, give you minus 2. Then what is lambda 1? Lambda 1 must be equal to minus lambda 2, which is 2 in this case. And how about lambda 3? Lambda 3 will be equal to 1. Okay? So 1, minus 2, and 2 give you a solution to this system here without being all 0. Okay? So that's basically what linear dependence means. Okay? This was just one example to understand what this means in action. Okay. So what is linear independent? So if this means linear dependent, okay, then there must be something that means linearly independent, which is when it's not linearly dependent. Okay, so let's rewrite down the definition of that. Let's do it on the side so we understand. We can compare with the other. Okay, so B1 Bk is linearly independent. So the system, or the set. Sometimes you say system for a set of vectors. Traditionally, it's also called a system of vectors. Okay, we say that the system of vectors is linearly independent. Okay, or Li. Going fast. If and only if it's not linearly dependent. Okay, it's kind of funny because it's not very useful unless I give some more explicit way of understanding not linearly dependent. So let's look at the definition of linearly dependent, okay, which is this one here plus everything that's coming before, so the whole sentence. Okay, and let's rewrite it maybe. So it means this: it's not the following. Okay, so this means let's write not. So what I've written there is this very quickly. It says if lambda is this, and I'm going to use the concentrated notation. Okay, that's what I've written here. Okay, it says that for some there is a lambda, there exists a lambda, which is non-zero, and v lambda. So if you want, there exists a vector lambda, which is non-zero, and v lambda is equal 0. Okay? So how do you negate this statement? Well, there's many ways of negating it. Okay? One of them is to say that for any lambda that is different than 0, then v lambda has to be different than 0. Okay, that's one way of negating. But there's more, so one way to think is this. Is if V lambda is different than 0, then V lambda is different than 0. Okay, but sometimes the contrapositive of this is actually more useful. Okay, because we don't like to deal with not equal. Okay, not equal is hard to deal with algebraically. So it's nicer to deal with equal. So if you have a statement like this, something not equal implies something not equal. It's the same thing as saying, okay, same as, you just take the contrapositive. Okay, so let's take the contrapositive of this. It says that V lambda equals 0. It implies what? Remember contrapositive? A implies B is equivalent to not B implies not A. Right? So this means that V lambda equals 0 implies it equals 0. In other words, in more kind of like human words, this means that the only way to nullify the linear combination, remember this is a linear combination of the form of this form here, okay, that's just a quick way of writing this, so I don't have to write summations all the time, okay. The only way to make this 0 is to take all the coefficients equal 0. Okay? That's what linearly dependent means. Okay? So let's see an example in the same spirit as this one. Okay? So let me just change the last vector. Okay, so let me take here a vector which is 0, I don't know, 2. We had 2 earlier. Okay, I'm going to put a 1 here. Okay? And let's first, okay, so let's rub this off and see what we're having. Okay, so. So when we say that these vectors, we try to understand what it means. So we try to understand if they are linearly independent. First thing is, let's draw a picture, okay? Because we're in 3 dimensions, the luxury of being in 2 or 3 dimensions, and we can draw pictures and think of them, okay? You cannot do that in 4, 5, 6, and all the other dimensions that are above, which are infinite. But this helps you understand what to do in those dimensions. Okay, so let's do it in the picture first. Okay, so V1, V2 haven't changed. The one that has changed with respect to the previous example is V3. Okay, so V3 now is 1, 2 in the second axis, and it's 1 in the third axis, right? So it's here. So in fact, it's lying on this plane, on the out of plane, right? Okay, so out of plane means when it's going towards you, right? That's my convention for drawing 3 dimensions. Which is not everyone, okay, because many people prefer to do the horizontal one and then go up in the 3rd dimension. It's a question of choice, okay? This is not. Okay, so this is basically 1, 2, and this is 1, and this is my vector. V3, yeah? Okay? So now you can see that the vectors, instead of, they don't lie on any common plane, right? Because these two are on this plane, right? And V3 is out of that plane, right? So this is, we already know from like elementary geometry that this means that they are not coplanar. So basically the points 0, V1, V2, V3 form a tetrahedron. Okay, tetrahedron is like a 3-dimensional triangle. Okay, it's something with 4 vertices. Okay, but before, in the example, the tetrahedron was squished on the plane 1, 2. Right, it was just squished here. Okay, whereas here the tetrahedron is not squished. Okay, so if you draw a tetrahedron around these points, okay, this is truly 3-dimensional shape. Okay, so that's what linear independent means. Okay, that we truly have 3 dimensions, so we can reach that. Okay, so in a sense, independence is like the most powerful thing that you can have for a system of vectors. Okay, because then the linear combinations of these vectors are the most efficient. Okay, in a sense that I will explain. Right, but you can see it already here. That this kind of efficiency means that the solution of the linear system is the same as earlier. Okay, same construction, but different coefficients. Okay, in this case will be unique, whereas there we didn't have a unique solution, right? I mean, the previous example, if you look at it, we noticed that the 0 solution is 1, but then we also found a non-zero solution. And remember, the solution that we found, actually we could have found infinitely many solutions, right? If you change the parameter lambda, you find another solution. Okay? And how many choices for the parameter lambda 2 do you have? Infinitely many, you know, as many as there are real numbers. Okay? So in fact, you have a whole line of solutions. Okay? Which is a subspace, which is something we've seen earlier. Okay, so this is how things are all connected, right? So in order to see that, let's write down very quickly as an exercise the linear system that comes out from linear for the requirement for linear independence or dependence, which is the same thing. Okay, so the requirement is this. So let's check. Let's check. What happens to the linear system v lambda equals 0? Okay, at this point, we understand that this is basically what we have to do every time we want to understand linear dependence or independence. Okay, so let's look at v lambda equals 0. Okay, so what is this? Well, this is, as I did it before, this time I'm going to go a bit faster. Okay, so it's 1, 1, 1, 0, 2, 1. Okay, times lambda 1, lambda 2, lambda 3 equals 0. Okay, this is the 0 vector, which means 0, 0, 0. Right? But you see this matrix here, as we've seen earlier, now this system, or the matrix, which is the same thing, okay, is upper triangular. Okay? So what is the algorithm to solve an upper triangular matrix or system? It's to use back substitution. Okay, so back substitution means that you start from the back and then you go backwards. Okay. So what does it mean for lambda 3? Okay, so back substitution, okay? Okay, so this is an upper triangular. Upper triangular. Okay, so the answer to the upper triangular system is back substitution, okay, which is simply to go backwards. Okay, so by back substitution, what do we know? We know that lambda 3 is equal to 0. This is the third equation. Okay, so third. There's not much to do here. Okay, we already know that lambda 3 is equal to 0. So back substitution with 0 right hand side is a piece of cake, right? Because all you need to do is to go back up. In fact, you realize very soon that you don't even need to solve anything. Because if you have an upper triangular matrix such that all these elements on the diagonal, so all the diagonal elements are non-zero, then you know that the only way to solve the system, matrix times vector equals 0, is to take the 0 vector here. Okay? That's something, it's an important result in linear algebra. In terms of the matrix is invertible. Okay, so we haven't done there. Okay, but this is basically the reason why it works. Okay, so back substitution, and you see it in the algorithm. Okay, so when I wrote down the algorithm for back substitution, you had this kind of like recursive. I wrote it in a recursive way. But you could also write it for loop. Okay, and every time I was checking that the coefficient on diagonal is non-zero in order to invert it. Okay. So say we had some other number here, so say 2, okay, it would be the same thing. It would be 2 lambda 3 equals 0. Okay? And say we didn't have a 0 here, say some number a, then all we had to do is to divide by that number. Okay? And then you go up. Why? Because you already have lambda 3, okay, and you substitute it here. Okay, and then you solve for lambda 2. And then you have lambda 2 and lambda 3, and you substitute them in here. That's back substitution. Okay? So here, back substitution is not really needed. Okay? This is from the second equation. I'm just doing it very, very slowly in order to understand this is the first equation. So in fact, this expression here equals 0 implies that lambda 3, lambda 2. So therefore, this is the only solution. Okay? Hence, 0 is the only solution of the system. And therefore, this conforms to the idea that V lambda equals 0 implies lambda is equal to 0. Okay? And therefore, we can declare these 3 vectors to be linearly independent. And geometrically it means that they okay. So another concept that is very important is the concept of span. Okay. So what is the span of a system of vectors? So given again, so in the vector space V, a finite given a finite set of vectors Vk. So same ingredients as for linear dependence or independence. Okay. Now I'm looking at the set, the span or space span. Okay, so this is just a quick way of saying space span or generated in fact, it should be called a linear span, okay, but we use it so often that we just say the span, okay, and we use mostly linear algebra, okay, and to be precise, I should say linear span, or the space span, or generated by the span of this system here. I'm going to write it very quickly as V, okay, where V I'm going to order them, okay, because sometimes it's handy to have them ordered, okay. But of course, if I shuffle them around, okay, I get another matrix. The situation is completely the same. Okay, is the set of all possible linear combinations by using these vectors here. Okay, so a set of all possible linear combinations. Okay, so basically, I go through all the lambdas in Rk. Of course, there's infinitely many, okay, but in my mind, I can do that, right? And then I collect the result of all these operations, all the outputs. Okay? This set here is called the span. Okay, and it's also denoted as, there's a notation for that. Which is span of V. Actually, I'm going to talk about physicists in general vector spaces. Yeah? The span of V is the sum of all those linear combinations. Okay? So let's see in our example. For example, what was the, just very intuitively. Okay, so let's go back to the initial example, and I'm going to do it with a yellow chalk. So this is the old V3. Okay, does everybody distinguish these four colors? Yeah, do you distinguish them? Yeah. Okay, thanks. Yeah. Well, not everybody does. Okay, some people don't distinguish the colors. That's why I asked you. Yeah. So let's take the V1, V2, and V3 old. Okay, these three together. Okay, and let's take all the possible linear combinations of these. What do you expect to get geometrically? Remember, linear combination means that you're scaling one, scaling the other. So you're scaling this one, say by this much, okay? Scaling this one, say by this much, okay? And then scaling this one, say you're going to shorten it just because it's more, it's handy, okay? And then you do the parallelogram for this one here, you get the result, okay? And then you do the parallelogram for this one here, and then you get some result, which is out of plane, something here, right? And so on and so forth, okay? So you change. So what are you going to get? You're going to get the plane. You're never going to be able to get out of that plane if you go into space. So what you get is the plane, right? So one of these three vectors actually is redundant. Okay, so in fact, linear dependence is exactly that. It's like linear redundancy. Okay, so one of them is redundant. We know that one of them is redundant because we know that V1, V2 by themselves would span the same plane again, right? We know that because they're not parallel, right? And also, if we took V2 and V3 old, we also would get the plane, right? And if we took V1 and V3 old, also we would get the same plane. Okay, so there's no one pair that is better than the others. Okay, they're all three the same. Okay? So it's not that one of them is bad. It's the whole three together that are bad. It's just like there's one too much. Okay? Now if you take V1, V2, and V3, what is the span of V1, V2, V3? It's all the possible linear combinations, and in fact we recover R3. Okay? Why? Because we have a vector that is sticking on the plane. So we can reach any vector in space. So even if we had a vector here, okay, then we would project it on the green axis first. Okay, we get one coordinate. Okay, and then we project the rest on the plane, and we get two more coordinates. Okay, so in fact, when we're talking about linear independent vectors, in fact, that's physically that means a reference frame. Okay, so all we're doing here is the same thing as you do in geometry when you're talking about reference frames, geometry or physics. Okay, so in mechanics you have a reference frame, means that you're putting a set of linearly independent vectors, and furthermore, that set of linear independent vectors must generate or span the whole space. Okay. Now, this is not telling you that the span of V has to be the space you started from. It's just telling you you get something, which happens to be a subspace of V. Okay. It might be V, but it might be something smaller than V. Okay. So let's show that. Let's check very quickly that we have a subspace. Okay. So that's indeed the case. Okay. So let's do it here. So we have the following proposition. The span of V, okay, for any finite, finite V. So here I'm gonna start kind of like identifying a set of vectors with a matrix or the array given by that set as a row. Okay. So the row of vectors V and the matrix V and the set V is the same when it's a finite set. Okay, it's just quicker to write everything. Okay. So for I V in V is a subspace. Okay, so proof. So let's remind ourselves. Okay, so recall. We say that W is a subspace. The V. So what is the? Do you remember what's the definition of subspace? So a subspace is essentially a subset that is closed with respect to linear combinations. So this means that if you start with two, it's enough to start with two vectors in W. Okay, so means that if say V and W belong to W, okay, and alpha and beta belong to R, then the linear combination alpha V plus beta W stays in W. Okay, that's basically what subspace means. So let's prove this. Okay, so consider V and W being span V, okay, because that's what we want to show. We want to show that the span of V is a subspace, so it plays the role of W in this definition. Okay, so let's pick two elements there. Okay, so how can we write that? Remember the span of V. So this is the span of V1 Vk. Okay, then it means that each one of these vectors can be written as a linear combination of those k vectors there. Okay, then V is equal to a linear combination. Let's call it lambda 1, lambda I, Vi. Sorry, okay, so I could also write lambda 1 V1 plus dots plus lambda K Vk, okay, which is written like this. But I can even concentrate this one here as this. Okay, so V is nothing but capital V times lambda, okay, for some lambda. So where do I take lambda? Lambda is an arcade, right? And W, same thing, okay, so I'm not going to rewrite the whole thing. Right? So W is V mean for some. Okay? Pick any alpha and beta in R. Okay? Pick any alpha and beta in R. So I want to show you that the linear combination, okay, so I want to show that alpha V plus beta W also belongs to the span of V. So it also belongs to W. Okay, I want to show that it also belongs to the span of V1. So in fact, I want to show that this is equal to V ni. Okay, this is Greek letter ni. It's not a V. Okay, so that's differentiated by more. Okay, so I want to show that this is equal V ni for some choice of means, yeah? Coefficients. Okay, so for some okay, that's what I want to show. Well, let's write down what we know already. Okay, so indeed, alpha V plus beta W is nothing but alpha times V lambda, right? Plus beta times V mu. Okay, this is, remember, this is, don't be scared by this expression. This just means like a very quick way of writing something like that. Okay, it's boring to write this all the time. So I'm writing it like this. Okay, that's why we introduce matrix notation. Okay, it's just a quick way of writing linear combinations. Okay, and we know that there are some rules of algebra. Okay, which we have identified last week. Okay, that tells you if you multiply by a scalar a matrix, then you can actually it's associative and commutative. Commutative when you have a scalar. Only in the case of scalars is commutative. Okay, two matrices in general do not commute. So if you multiply matrix A with B, it doesn't mean that you get the same result as B times A. But if one of the two matrices is a scalar, then it's okay. Okay? So this is because scalar multiplication. Scalar scaling. Okay, so scalar multiplication is a very confusing thing. We said we will never use it. Okay, so scaling means multiplying by a scalar. Okay, which actually where the word comes from. Okay, to scale something is to make it bigger or smaller. Okay, when you're scaling something, it means that you're making it you're multiplying by a factor. Okay, by a common factor to all directions. Okay, which means alpha. Okay, so this is V times alpha lambda, okay, plus V times beta mu. Okay, so make sure you understand all these steps, okay, by looking into the details. Okay, so really write down this as indices, and you will realize that what we're doing here is not rocket science. In fact, it's quite simple. Okay. And then also this distributive law is satisfied, and therefore we're done. Okay, so basically we've shown that this one here can be written in the form V times nu. So in fact, the coefficients nu are nothing but the same linear combination. Okay, so basically there's some kind of correspondence between the linear combinations on the abstract vector space W, okay, which is, where is it? It's this linear combination here. Okay, so you see the form of this guy here is very much the same form as this one here. Right? The shape of this is the same as this. And in fact, if you think about it, lambda is the set of coordinates, if you want, of the vector V with respect to this kind of system V. Okay? That's basically what we're doing. Okay? This is the linear algebra counterpart that we're using the reference vector. Okay, so that's the span. Okay, now an important result about spans and linear dependent systems is the following. Okay, so let me state it in a concise way. Okay. It is. I'll take it also from my book. So suppose you have a linear system. So here. Suppose V1. Okay. R. Independent. And let W1, Wn be such that each single one of these belongs to the span of W. Okay, so a reminder, this is quick notation. So this means W1, Wn, okay? And we're saying that V R belongs to this, or any R to K. So these guys are all in this vector space, which is, we know it is a vector space from here, okay? Then V1 Vk can be extended to a system of the form E1, K, and then they have some extra vectors. I'm going to call them U1 all the way to UN minus K. Such that the span of this system, okay, point of view, okay, the span of U is equal to the span of W. So basically, what this is saying, it's saying that you can build a list of linearly independent vectors that will span the space, provided you add some stuff to it. Okay, you may have to add, but you may not have to add depending on m. Okay, so if m equals k, then you can stop. You don't need to add anything. Okay, and this is telling you basically something quite important about vector space. It means that every vector space that is spanned by a finite number of vectors, in fact, can be spanned by linearly independent finite number of vectors. Okay, so from any spanning set, we can go to a linearly independent spanning set. Okay, so a linearly independent spanning set is such an important concept that has a name. Okay, so before we prove this, okay, so definition: a set of vectors that is it has two properties. Okay, that satisfies two. So it satisfies vectors V. Okay, that satisfies. And let's do it just only for finite sets. Okay, this works also for infinite sets, and that's why I always forget to say finite. Okay, but let's take a finite set of vectors V. It satisfies one. The first property is that span of V is equal to some vector space V. Okay, and two, V is linearly independent. It's called the basis of V. Okay, it's called. Okay, this is the definition of basis. So basically, a basis is something that is both a spanning set and linearly independent. Of course, basis of something, right? Because any linearly independent set is the basis of the span, right? Of itself. Yeah. So what I have in context here, what I have in mind here, the context is that I start from the vector space V, for example, Rn. Okay, and I ask myself, can I find a basis for Rn? And the answer is, because of this theorem here, yes. The answer is yes. You can find a basis. Okay? Alright. So maybe we should take a break here, okay? And then we'll reconvene in 10 minutes to prove this theorem. Okay? Okay, so